Hello everybody, and welcome to our video on calculus with parametric curves. So we're really just going to talk about the sort of standard problems that we want to solve using calculus. So derivatives, area problems, things like that, but within the context of these parametric equations that we talked about in the last video. So first let's start with tangents. Well, we need a new formula for the first derivative for parametric equations. So let both x equal f of t and y equal g of t be differentiable in terms of t, and y also is differentiable as a function of x. So we've got both of these functions differentiable with respect to t, and y itself is also differentiable with respect to x. Then the chain rule gives the following: dy dt equals dy dx times dx dt, so that's pretty standard. And therefore, if we just divide out dx dt, assuming that it's not equal to 0, then we get dy dx equals dy dt divided by dx dt. So pretty simple derivative rule for parametric equations. Now, when we look for second derivatives for parametric equations, of course, that's just the derivative of the first derivative, right? So we are applying the derivative with respect to x, again, on dy dx. But in the context of our formula, all we've done here is taken our function y and replaced it with the derivative, dy dx. So the second derivative looks like the derivative with respect to t of dy dx divided by dx dt. Okay, so let's take a look at an example here. Example 1, find an equation of the tangent to the curve xy equals t minus t to the negative first power and 1 plus t squared at the point corresponding to t equals 1. So in order to find an equation of the tangent to the curve, we first need to know what the derivative is at that point. So that also means we need to know what point we're talking about. So for t equal to 1, what do we get? Well, we get xy equals 1 minus 1 and 1 plus 1. So that's just 0, 2. So there's our point. Now we need to have a derivative function in order to evaluate this derivative at the point. So we're just going to use our derivative formula here. So x equals t minus t to the negative first power. So dx dt equals 1 minus negative 1 times t to the negative second power, which is just going to be 1 plus t to the negative second power. Now y, on the other hand, is 1 plus t squared. So dy dt is equal to 2t dt. And therefore, if I want dy dx, I can just divide these results. Dy dt divided by dx dt, which gives us 2. I should not have put dt there. That was accidental. Gives us 2t divided by 1 plus t to the negative second power. So now we want to find the derivative at this point. So this is dy dx evaluated at 0, 2. So keep in mind this isn't times, right? We're evaluating at this point. But at this point, we're talking about t equals 1. So we'll just plug in t equals 1. That's 2 over 1 plus 1. It's 2 over 2, which is 1. So finally, in order to find the tangent line, we just need to use point-slope form here. So y minus y1 equals m times x minus x1. So that's y minus 2 equals 1 times x minus 0. Remember, we're just using that point we found earlier, 0, 2. And this gives us y equals x plus 2. Okay, so now that we're done with that example, let's move on to one more. Find dy dx and the second derivative of y with respect to x. For which values of t is the curve concave upward? All right, well, first we'll need to find dx dt. Since x is t cubed plus 1, that's just going to be 3t squared. And we'll need dy dt. So that's just going to be 2t minus 1. So the derivative of y with respect to x is what we get from dividing dy dt by dx dt, which is 2t minus 1 over 3t squared. Now we want to find the second derivative. So that second derivative, remember again, the same formula, except in the numerator, instead of taking the derivative of y, we're taking the derivative of dy dx. So dy dx is 2t minus 1 over 3t squared. So here we've got to apply the quotient rule. All right, so we've set up our quotient rule. Now we'll just evaluate these minor derivatives here. We get 3t squared times 2 minus 2t minus 1 times 6t divided by 9t to the fourth. Now instead of dividing this whole thing by 3t squared, I'm going to write this as multiplied by 1 over 3t squared. And let's simplify what we have in this numerator up here a little bit. So we've got 3t squared times 2, that's 6t squared. And minus 2t times 6t, that's minus 12t squared. And then let me say that again. Negative 1 times negative 1, that's positive 1 times 6t, so plus 6t. And in our denominator, we're going to have 27t to the 6th. Okay, so first we've got this 6t squared minus 12t squared. That's negative 6t squared plus 6t divided by 27t to the 6th. Factor out a 3 and a t up top. Comes 3 times t times negative 2t plus 2 divided by, and now I can pull, I'm just going to rewrite 27 as 3 times 9 and t to the 6th as t times t to the 5th. So we can cancel this out in front, and we get left with negative 2t plus 2 over 9t to the 5th. Okay, so now let's try to answer this final question here. For which values of t is the curve concave upwards? So let's just think back a little bit to some calculus 1 here. We've got a curve that's concave upwards, so what does that mean? That means that the derivatives are increasing. So dy dx is increasing, which means the second derivative is positive. So that's all we're trying to check here, is that the second derivative is positive. Now there's a little bit of complication here, because our numerator and denominator both contribute to whether or not this number is positive. So for it to be positive, either both the numerator and denominator need to be positive, or both need to be negative. So either negative 2t plus 2 is positive and 9t to the 5th is positive, or negative 2t plus 2 is negative and 9t to the 5th is negative. So these are a little bit different, right? If either of these two statements is true, then the whole thing is positive. But within each statement, you have two conditions that contribute to it. So here, we subtract 2 and then divide by negative 2. So that inequality is going to flip when we divide by the negative. So we should get t is less than 1. So yeah, negative 2 divided by negative 2 is 1. But the inequality flips. So t would be less than 1. And t would be greater than 0. So for both of these things to be true, t just has to be strictly in the interval from 0 to 1. So that's one possibility. Or, in this case, t would have to be greater than 1, right? We subtract negative 2, divide by negative 2, the inequality flips, so t is greater than 1, and t is negative. But this is not possible. T can't be greater than 1 and negative at the same time. So this condition can't be met. So the only condition that matters here. So t has to be between 0 and 1 for the graph to be concave upwards. Okay, so let's take a look at another example. Find the points of the curve where the tangent is horizontal or vertical. So if the tangent is horizontal, that means that the derivative is 0. And if it's vertical, that means the limit of the derivative is infinity or negative infinity. And generally, we're going to check for that by looking for a place where the derivative doesn't exist. So let's go ahead and start calculating this thing. dx dt is actually, I should say dx d theta. Our parameter here is theta. We've got e to the sine of theta for x. So when we take the derivative, we need to apply the chain rule here. So we get e to the sine of theta times cosine of theta, which is the derivative of sine. And dy d theta is e to the cosine of theta times, now the derivative of cosine is negative sine. Okay, so there we go. So dy dx is going to be dy d theta divided by dx d theta. So that's negative sine of theta times e to the cosine of theta over cosine of theta times e to the sine of theta. And I just rewrote those multiplications. Now this gives us negative tangent of theta times e to the cosine of theta minus sine of theta. Right? We just used our power rules. here. Or I should say exponent rules more properly. All right, so what do we know here? Well, we know the exponential function, this thing here, is always strictly positive. So it's not going to contribute to whether or not the tangent is horizontal or vertical directly. So really all we're concerned about is tangent of theta. So dy dx is going to equal 0 when tangent of theta equals 0. And so that's any theta where, well, so tangent of theta is 0 when sine of theta is 0. So that's going to be at 0 or pi or 2 pi. So that's any integer multiple of pi. So that means if theta is any integer multiple of pi, that means x is e to the sine of some integer multiple of pi. And y is e to the cosine of some integer multiple of pi. Now, this derivative doesn't exist, and in particular approaches plus or minus infinity, one or the other, when tangent is approaching plus or minus infinity. Okay, and in that case, that's when cosine is 0, right? The tangent is sine divided by cosine. So when cosine is 0, that's when tangent is approaching plus or minus infinity. So those cases are going to be pi over 2, 3 pi over 2, 5 pi over 2, etc. So this would give us theta is pi over 2 plus any integer multiple of pi. So, in other words, the cases when the curve is horizontal is for these x and y coordinates, e to the sine of pi n and e to the cosine of pi n, respectively. And it's vertical in the cases where x equals e to the sine of pi over 2 plus some pi times n multiple, or y equals e to the cosine of pi over 2 plus some pi times n multiple. Okay, so let's move on away from tangents and move on to areas. So this is a slightly more complex problem. Let's just take a look here. So first we're going to consider, of course, the case where y is positive, because usually when we're talking about areas, we want to restrict to positive areas above the curve. So here we're considering a function, y equals cap f of x, which is strictly greater than or equal to 0 for all x between a and b. And in general, we would say that the area is the integral from a to b of cap f of x dx. But it might be that we have this curve expressed parametrically and not in Cartesian standard equations. So if that's the case, then we need a way to be able to evaluate in terms of parametric equations. So if we consider the same curve, but expressed parametrically, where y is equal to g of t and x is equal to f of t, and f of alpha equals a, and f of beta equals b. So in other words, when you translate your x coordinates under t equals alpha and t equals beta are the t that correspond to x's a and b. And g of t is really just cap f of little f of t, which is cap f of x, right? So all we're saying here is this function that describes y, it's the same function that we had before, but we've replaced x with its function f of t, its parametric function. So if we substitute this in, that means cap f of x equals cap f of little f of t. And dx is just f prime of t dt. So if you think about that, x equals f of t, so x dx dt equals f prime of t. So if I multiply dt across, I get dx equals f prime of t dt. So nothing crazy there. We've changed our bounds accordingly based on this substitution. And now we've re-expressed cap f of t as g of t. So that's identically what it was, right? We just are re-expressing it in our parametric notation. So in other words, we get that this integral is the integral from alpha to beta of y of t times dx dt times dt. So if we have the parametric equations, then we can just take our integral from alpha to beta, y of t times dx dt times dt, and integrate that. Now, we did assume that alpha was less than beta here. Now, it could be that when you translate, like if your curve is moving from right to left, it could be that when you take that translation from right to left, that you actually get alpha and beta that are switched around, where beta is less than alpha. So if that's the case, you would just integrate from beta to alpha so that you were still integrating from the left side to the right side. Or you were, I should say, you were integrating within the parameter from smallest to largest. Now, if you wanted to find the area along the y-axis instead of along the x-axis, so what we did here was, right, we found a formula for our standard curve. So if instead you wanted to find an area along the y-axis, so some curve that looked like this, then nothing really changes here, except that you switch, instead of y of t times dx dt, you would have x of t times dy dt. Okay, so let's take a look at an example of these area problems. This one has something kind of tricky going on that we'll see in a moment. Now, the first thing to recognize, it asks us for the area enclosed by the curve and the y-axis. So as we mentioned here, that means we've got to switch x of t and y of t around, right? But that's actually not quite enough here, because if we just do that, we're not going to get the correct answer. We have to recognize that the curve we're looking at here is actually not going to be on the right side of the y-axis. So normally, right, if we had the right side of the y-axis, something like this, or even maybe it intersects like this, then this would be the case where we would consider the integral of x of t times dy dt. Remember, we'd be switching that around. But that's not quite correct, because if we take a look at this function here, well, first let's find out. It says enclosed by the curve and the y-axis. So if we just first ignore this graph, this is just a general sketch. So if we take a look at this parametric function here for x, when is x equal to 0, right? Because that's where the y-axis is, so that tells us when this parametric curve intersects the y-axis. So that's t squared minus 2t equals 0. So we've got t times t minus 2 equals 0. So t equals 0 and t equals 2. Now, that tells us that when t is 0, x is 0. What else do we get? Well, we get y is 0. So let's plot that point. T equals 0. And when t is 2, x is 0, but also we get the square root of 2 for y. So for good measure, let's plot one more point and see what happens. Let's plot t equals 1. So we get 1 minus 2, that's negative 1. When t equals 1, we get negative 1, 1. So that puts us over here. So this isn't exactly what the curve looks like, but it gives you a rough enough idea that the curve is actually on the left side. So our integral will calculate these as negative values, but we were asked explicitly for the area, which should only be positive. So that's easy enough to deal with. So what we'll do is take our integral, alpha to beta, and instead of it being x of t, it'd just be negative x of t. All right, that's going to take this and make the whole thing positive. Now let's start plugging that stuff in. So this is the integral from 0 to 2. Those are our t values. Negative t squared plus 2t, right? I'm just distributing that negative right away. Now, this square root of t is y, so if y equals the square root of t, which is t to the 1/2 power, then that means dy dt equals 1/2 t to the negative 1/2 power. Now, before I go any further, I just want to point out that this is a perfect example of why it's pretty important to get at least a rough sketch of your parametric equations before you try to set up your integrals to find their area, because it's very easy to end up in a situation like this where you get an answer that doesn't make sense because you haven't considered that the graph is actually on the left-hand side of an axis, or if it was the x-axis underneath. Okay, so let's distribute this expression here across. What do we get? We get, well, t squared times t to the negative 1/2. So this is negative t to the 3/2 divided by 2. Plus, now the 2's cancel, and I get t to the first power times t to the negative 1/2. That's t to the positive 1/2 dt. So now when we integrate, we get negative t to the 5/2 over 2 plus t to the 3/2 over 3/2. Did I say over 2? That should be over 2 times 5/2. All right, so we increased our power to 5/2. We divide by the new power. Same thing here. We increase the power to 3/2 and divide by the new power. And now we're going to need to evaluate all of this from 0 to 2. Let's do a little bit more simplification while we're at it. This 2 over 2 cancels. And over here, dividing by 3/2 we'll rewrite as multiplying by 2/3. So this is really negative t to the 5/2 over 5 plus 2/3 t to the 3/2 from 0 to 2. Okay, we plug in 2, we get negative 2 to the 5/2 over 5 plus 2/3 2 to the 3/2. And when we plug in 0, we're just going to get 0, so that doesn't matter. This is negative. Now 2 to the 5/2 is 2 squared times 2 to the 1/2. Two to the 3/2 is 2 times 2 to the 1/2. So over here, this gives us negative 4 times the square root of 2 plus 4 times the square root of 2. But this first one is divided by 5 and the second is divided by 3. Now we can factor out this 4 times the square root of 2. And inside we can rewrite this as 1/3 minus 1/5. So the common denominator here would be 15. So this would be 5/15 minus 3/15, which is 2/15. So this all becomes 8 root 2 over 15. All right, that's it for example 4. This is a little bit of a tougher one. You really got to watch out for interpreting that graph correctly. So let's move on to the problem of finding arc lengths. So you may recall from Calculus 2 that we found the length L of a curve C, where the function was in the form y equals cap f of x for x between a and b with a continuous derivative. That L was the integral from a to b of the square root of 1 plus dy dx squared with respect to x. Now, suppose that your curve can instead be expressed by parametric equations, x equals f of t and y equals g of t, for t between alpha and beta. Again, where you have a derivative of x with respect to t, but with the added requirement that this derivative is positive. So the derivative exists and it's positive. Now, this requirement that f prime of t is positive adds the extra condition that the curve is traversed only once from left to right as t increases from alpha to beta. Right? If this derivative is positive, that means x is increasing along the curve as t increases. And additionally, f of alpha equals a and f of beta equals b. So now let's take a look at our original formula. Now, dy dx we know can be rewritten as dy dt divided by dx dt. And this whole thing is squared. Now we've got this dx we've replaced with dx dt times dt. And in this next step, what we're doing is squaring it and taking the square root. Since we know that derivative is positive, the square of its square root will be the same as the original derivative. And that lets us move it into this square root together with the rest of the expression. Now, when I distribute dx dt squared, it cancels this denominator here. And then when it multiplies by 1, leaves me with just dx dt squared plus dy dt squared, all inside the square root. So, in other words, for parametric equations with x and y, we've got L equals the integral from alpha to beta of the square root of dx dt squared plus dy dt squared, all with respect to t. All right, so let's take a look at an important summary of this, right? So we're summarizing this whole thing. Let's just make sure it's super clear what we're saying the requirements are here, because remember, you can't apply these theorems unless the requirements are met. This actually perfectly ties into what we looked at before, right? We can't use this formula exactly because there's an implicit requirement that x would have to be positive here, right? Because the requirement here was that y was positive. So here we had to make it positive by multiplying by this negative x of t. So we might have to adjust things a little to fit the theorems that we're working with. So if a curve C is described by the parametric equations x equals f of t and y equals g of t for t between alpha and beta, where f prime and g prime are continuous on the interval from alpha to beta, and C is traversed exactly once as t increases from alpha to beta, then the length of C is L equals this integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. Okay, so let's actually apply this a little bit and set up an integral that represents the length of the following curve. So x equals t squared minus t and y equals t to the fourth for t between 1 and 4. Now I'm going to need each of their derivatives. So let's start out by taking dx dt. That's going to give me 2t minus 1. And dy dt is going to give me 4t cubed. So then L will be the integral from 1 to 4 of the square root of 2t minus 1 squared plus 4t cubed squared dt. Now, some of these integrals that you can get, if we multiplied this out, we'd get a polynomial to the 6th power. It's not really something you can practically do usually, except for in very special cases where the algebra works out nicely, which you would have seen some examples of that in calculus too. But that's not always the case. Sometimes they're not really practical, so we have to use approximation methods. And usually at that point, once we have an integral that represents the length, then we can turn to a computer to say, okay, here, calculate this approximation for me. Really what we need to be able to do for a problem like this is just set up the approximation in the first place. Okay, so let's take a look at this example, find the exact length of the curve. So similar problem, but this time we've got to actually work out all the details. So we're going to start the same way by finding dx x dt. And that's going to be e to the t minus e to the negative t. That's just the chain rule there. And dy dt, that's just going to be negative 2. Now L is going to be the integral from 0 to 3 of the square root of e to the t minus e to the negative t squared plus negative 2 squared dt. Okay, so what do we get here? We get e to the 2t, because e to the t squared is e to the t times e to the t, which is e to the 2t. Minus, now here we get e to the negative t times e to the t. So those cancel and just leave you with 1, because this is the same thing as 1 over e to the t. So we get minus 1, and then minus 1 again, right, for the second time that pair gets multiplied, plus e to the negative 2t when the last term multiplies by itself. And then don't forget we've got this negative 2 squared, so that's plus 4. So notice that this middle term here is actually minus 1 is actually minus 2, right? So when we add this 4, we're going to get e to the 2t plus 2 plus e to the negative 2t. And so you might notice that that has to then factor to basically the same thing here, except plus in the middle instead of minus. So this factors to e to the t plus e to the negative t squared. And since this is something squared and you're taking the square root, we just get the integral from 0 to 3 of e to the t plus e to the negative t. And for some reason I wrote that bound down wrong. Let's change that. That should be from 0 to 3. There we go. So when we integrate this, we get e to the t plus e to the negative t divided by negative 1. That would require the substitution rule, but it's a pretty straightforward substitution. And evaluate this from 0 to 3. This gives us e cubed minus 1 over e cubed minus e to the 0, which is 1, minus e to the 0 again, which is 1. Those cancel, and we're left with just e cubed minus 1 over e to the third. All right, that's it for this section. Thanks for watching.